Hello everyone. Today we're going to talk about composite functions, or FOG, which is a little funny. If it were up to me, I might have included these first two sections of chapter 5, which are composite functions and inverses, back when you would have talked about functions before, which I believe was chapter 2. And the reason for that is they're just kind of basic function properties, kind of like the addition of functions or subtraction of functions. But they're included here in chapter 5 because in chapter 5 we're going to talk about exponential and logarithmic functions. And those two are inverse functions of each other. Now, when I said fog here, that wasn't entirely a joke. If I have two functions, f of x, let's do 2x plus 1, and g of x equal to x squared minus 2, then what you may have learned in chapter 2 is that, well, you can create a new function, h, by, say, adding these two together, or subtracting them, or multiplying them, or whatever. But when we do a composition of functions, say fog there, the notation is f little circle g of x. What this actually means is I'm plugging one function into the other, and it's always the second that goes into the first. So what this means is f of g of x. And the notation on the left there is really just a condensed notation, so we don't have to write as many parentheses. So what this is going to look like is, well, we're looking at f of g of x, that's x squared plus minus 2. And when I plug x squared minus 2 in place of x for f, I get 2 times x squared minus 2 plus 1 as a result. And I can multiply this out and see I'll get 2x squared. I'll have minus 4, but plus 1, so minus 3. And I can flip this composition around. GOF of x, I'll get g of f of x, which is g of 2x plus 1. And when I replace 2x plus 1 in place of x in g, I'll get 2x plus 1 squared minus 2, giving me really a totally different looking answer. Let's see what I get here. I get 4x squared plus 4x plus 1, but then minus 1 at the very end. Now, using composite functions, if I wanted to, say, evaluate fog at somewhere specific, there's two things I could do, really. Let's choose a different pair of functions for this next part. Let's let f of x be equal to the square root of x plus 1, and g of x equal to 3x. And let's list a bunch of things we want to find. We have f of g of 5, g of f of 3, f of g of minus 1, and then a couple of fun ones, GOG of 1 and FOF of 8. Now, it's true what I could do is I could say off here on the side, FOG of x would be f of g of x would work out to the square root of 3x plus 1, or GOF of x would be, let's see, 3, and I'm replacing x with f, so I'll have 3 square root x plus 1. And I could just plug in whatever number I need into these new functions. So I could, if I wanted f of g of 5, I could look at my f of g of x function over here and just plug in 5, and I'll get the square root of 15 plus 1, which is 16, and the square root of 16 is 4. So I should get 4. But another way to attack this is to say, well, look, this is f of g of 5, and then I'll just say that, well, g of 5 is equal to 15, and then f of 15 is equal to the square root of 15 plus 1, which is square root of 16, which is 4. So I didn't actually have to do the find the composed function. All I needed to do was evaluate it in steps. And we can do this for as many functions as there are. We're going to stick to 2 for now. So if I wanted g of f of 3, that's g of f of 3. But f of 3 is going to be square root of 4, which is 2. And g of 2 is going to be 3 times 2, which is 6. Which I think is a little bit easier than taking the extra steps to find the full composed function. Especially if you have a long list of composed functions, which can happen maybe as part of your work in calculus. But certainly I'll be sure to throw one at you guys at some point. Let's try f of g of negative 1. Let's see, we're looking at f of g of minus 1. G of minus 1 will be minus 3. F of minus 3 will be the square root of minus 3 plus 1, which is the square root of minus 2, which isn't a real number. Now for us, unless we specifically state we're going to work in complex numbers, we're never going to. And in fact, unless you stick with math long enough to take a class called complex analysis, you generally never use complex numbers, except for a couple of specific topics in calculus 3 or linear algebra. So the issue here is I tried to plug in a number that was not in the domain of the composed function, but there wasn't anything stopping me from plugging it into the first function, which was g. And we'll get into this in a bit, but basically the domain of a composed function is kind of an intersection of the range of one and the domain of another, as well as the domain of whatever. We'll get there when I get there. Now I can compose a function with itself. So here I've got a GOG. This is g of 1. G of 1 is 3, so I'm looking at g of 3. But g of 3 is going to be 9. In fact, if you were to compose these, GOG of x, we would have gotten g of 3x, which would work out to 9x. Because if we look at what g of x is it's a function that takes x and just simply multiplies it by 3. So if I compose it with itself, then I end up multiplying it by 3 twice. And for the same reason, we can do f of 8. This is f of 8, which is f of, well, the square root of 9 is 3, so this is f of 3 but f of 3 is equal to the square root of 4, which is 2. So let's talk about that domain problem that we had here. We want the domain of a composite function. Oops. And for our purposes right now, we're just going to be looking at f of g, a composition of two functions and no more. For example, so we're just going to do one. Let's consider f of x equal to x squared plus 1 and g of x equal to the square root of x minus 1. Now, if I wanted the domain of the composite function, f composed with g, f g of x, I could just find the composite function and then work at looking at the domain of the result. However, this can come with a little bit of risk. So let's see, f of g of x, we're looking at f of the square root of x minus 1, which is square root of x minus 1 squared plus 1. Now, if I were to do this and square it, I would get, let's see, just x minus 1, because the square and the square root should cancel, and then plus 1 giving me x. So it would be reasonable for me to say that the domain here is all real numbers, because x is a polynomial, and there's never anything wrong with polynomials. Except I would be wrong. It's not going to be all real numbers. And the reason for that is the inside function of the composition, it has domain restrictions. For example, even though these canceled and gave me a plain x, the issue is the inside function here, g of x, it has a domain restriction. So there we have some rules to follow, because I built this function out of two others, but what happened was there was a little cancellation here, which removed some of the restrictive information. This is kind of like the problem we had in, I think it was the last chapter, with asymptotes. We could have a factor on top cancel with a factor on the bottom, and it would look like it would delete the asymptote, but it would actually leave behind a little hole because that number for that factor still had to be cut out of the domain. So let's see. On the right, we have concerns about domain. One, any value not in the domain of G but I should say generally here, inside function. That's how I set it up in this problem up here. I had G on the inside. So where's my, there's my inside. If I can't plug in a number on the inside, then I can't get a result from that number on the inside, and so it can't be in the domain of the whole function. So any value not in the domain of G, or the inside function, must be excluded. And this is kind of the harder part. Any value x for which g of x is not in the domain. That's weird. Let's try that again. The domain of f. If I plug in a number for g and get a result, then that result needs to also be in the domain of f, because if I had these swapped around, for example, actually, this might be a bad pair for this example. So I'll come up with some more functions. Let me finish writing this. Any value x for which g of x is not in the domain of f must also be excluded. So for a nice function, or a nice composite function, like the one we have here on this page, if the outside function is like a polynomial, nothing ever goes wrong with polynomials. But some things do go wrong when we have square roots or rational functions, for example. And we'll have even more of these to put together later in the next class when we have trig functions, sine and cosine. But what's happening is the range of g, the inside function, the outputs, must fit inside the domain of f, the outside function. So let's see if I can cook up a pair, but that's not going to work for. This should be a good pair. Let's try f of x equal to square root of x and g of x equal to 1 over x. So if I look at the square root of x, the domain is, let's see, I have to be strictly positive numbers. I can't, oh no, it's not strictly positive. I can plug in 0. Okay, but no negative numbers. And then for g here, I can plug in anything that's not 0. So minus infinity to 0, union 0 to infinity. Now let's see, if I look at f of g of x, and I want the domain there, well, g of x is on the inside. It says I should cut out 0. So far, the way I'm looking at it is I'm going to have a domain that matches g of x. But from f of x, this says that g of x cannot be negative. So this should say g of x is greater than or equal to 0. Okay. So that limits me a bit, but what I end up with is the domain of f of g of x should be, let's see, I can't be 0, and I can't get a negative number as a result, which means I'm going to be stuck here with the numbers that are only going to give me positive numbers from g. So I'll have 0 to infinity. Let's move this down just a little bit. If I put together f and g, we can look at the domain a different way. F of g of x, this is equal to f of the square root, nope, I got these mixed up, f of 1 over x, which is equal to the square root of 1 over x. And this actually boils down to 1 over the square root of x. So this is actually kind of a fun pair of functions, because if I flip it around, go off on a tangent here, g of f of x, I actually get the same result. This is equal to, let's see, 1 over, I'll write it properly, g of square root of x, which is equal to 1 over the square root of x. This is a pair of functions where no matter how I compose them, I get the same function as a result, which is kind of nice, but it doesn't happen all the time. And if I recall, it doesn't really do anything too useful for us. But when I analyze the domain of this composed function here, I can see that, well, x must be greater than or equal to 0 because of the square root, but also x must be greater than 0 because it's in the denominator. Or rather, I should say, instead of just greater than, not equal to 0. And a combination of these rules kind of an intersection gives the result that x should be strictly greater than 0. So what we're kind of seeing here is, let's see if I can write it up here. I can't fit it up here. But let's see, the range of g of x it's kind of a nice function, is minus infinity to 0, union 0 to infinity. G of x is kind of a symmetric function like that. And it must fit inside domain of f of x, which is 0 to infinity. So I'm looking at an intersection of the range of one function and the domain of another, range of inside function, domain of outside function, and this intersection is only going to leave me with this part here. But I don't want to oversimplify the case I'm making here, because these are nice functions, square root of x and 1 over x, and if I have sufficiently complicated functions, it might not be this easy to analyze. If we flip this around, we can make the same kind of an argument for g of f of x. From f of x, I would have to say that, let's go ahead and write it actually, g of f of x, my domain, from f, the inside, we should always start with the inside. We need to have not negative. And then from g, we need f of x to not be equal to, not be equal to 0. Looking at it this way, I'm going to try to make sure that our problems are like this. Looking at it this way is, if we have just a few restrictions, we can solve for them. Do I have one? Let's see. So let's try this with another pair of functions here. When we have rational functions, we have very specific domain problems, just simple points. Other more complicated functions, like when we have maybe absolute values involved or square roots, it can be a bit more complicated to analyze. And at that point, when I have large gaps of my domain missing, then it's usually better to, I don't want to just say large gaps, but not in the sense that I've cut off half of the real number line. But if I have big gaps of the domain missing, then it's usually better to just write out the composed function and analyze the domain from that standpoint. Versus if I only have little singular holes, then it's best, or rather less work, to just look at the smaller domain problems of the composed function and build it from there. So what I mean by that is, let's take f of x equal to 2x minus 1 over x minus 2, and g of x equal to x plus 4 over 2x minus 5, and I forgot my line there. So what do you think? F of x or g of x? Let's do g of f, simply because we've always been writing FOG. Say I want the domain of g of f of x. Well, we'll need some information first. The domain for f, we like net rational functions because we only have to look at the denominator. We just have to be not 2, no other problems. The domain for g is x is not equal to, let's see, this is 5/2, 5/2. So from my list up here, oops, come on, scroll bar. We need to look at, we need to cut out the values that are domain problems for the inside function, and then we have to cut out values for which the result of the inside function is outside the domain of the outside function. I might have said that backwards. Let me try it again. We have to cut out values for which the result of the inside function is not in the domain of the outside function. So let's write out what that means. From the inside function, so let's see, from f, x cannot be equal to 2. And then from g, we're saying that f of x cannot be equal to 5/2. The result of the inside function can't cause a domain problem for the outside function. So far, this is an immediate domain restriction that we have because we're always basing it off of the inside. But also we need to solve f of x equal to 5/2, and we need to cut out all of the x values which cause f of x to be equal to 5/2. So let's say f of x equals 5/2, which means 2x minus 1 over x minus 2 is equal to 5/2. I can solve this by cross multiplying. So I've got 2 times 2x minus 1 equals 5 times x minus 2. So I get 4x minus 2 on the left and 5x minus 10 on the right. Subtract 4x from both sides. Add 10 to both sides. What do I get? I get 8 left over here equals x over here. So what this says is that if x is equal to 8, if I plug in 8 here, my f of x is going to give me 5/2. But when I try to plug in 5/2, I'm going to get a problem for g. So these are my two domain problems for this pair f and g of x. So let's write this. The domain is therefore excluding both of these values. So let's see, I can go minus infinity up to 2. I have to cut out 2. Then I can go up to 8. I have to cut out 8. And then I have to go up to infinity. And I'll leave you guys to actually write out what this composed function looks like on your own. So let's see what we've taken care of. We've got finding the domain of composed functions, at least for the nicer rational ones, that's down. And we've found out what composing functions actually means. But we also kind of have a Newton's law going here. One of the things in mathematics is every time we do something or find a way to do something, the next question is, well, how do we undo it? Which is kind of a big deal for things like cryptography or encryption, is like, hey, we can hide all this information by doing this. But the next question is, okay, but how do we undo it? How do I unencrypt whatever information I have? And thankfully, still, the answer is hard for cryptography because factoring numbers is a hard thing to do. Although it gets easier the stronger computers we have. Like right now, with our coronavirus thing, what do we got? This folding at home network, bunch of computers linked together through the internet to try to solve molecular medicine problems, they're currently at least 15 times stronger or more powerful than the world's most powerful supercomputer. It probably won't be too long till they become stronger than all the supercomputers together. But enough rambling. We are wanting to decompose now. This might seem like a strange thing to want to do, but this is actually a necessary skill, we'll say, for calculus, because in calculus we can take the derivative of simple functions kind of easily. The way calculus works is we solve some simple problems, and then we have facts to help us deal with more complicated problems. Let's not talk about limits right now because we don't like limits. But for derivatives, what we do is we use the definition to find the derivative of some basic functions, like, okay, what's the derivative of x? What's the derivative of cosine? What's the derivative of square root of x? And we can do all those things. But the more complicated the function, the more difficult it is to find the derivative using the definition. It can get very complicated very quickly if I have a ugly enough looking function, simply because the work involved would be kind of monumental. But what we do have is we have something called a chain rule, which says that if you can decompose your function into smaller pieces, then you have a very easy way of constructing the derivative. So this isn't without motivation. If I have a nasty looking function, maybe I can decompose it into simpler ones, and that will make my calculus jobs easier. So let's start with an easier one. One of the problems with decomposing is some non-uniqueness. Let's say this. Let's decompose the following functions into two or more simpler functions. That's weird. And I put simpler in quotation marks there because simpler is relative, and it can mean different things to different people. But let's suppose we've got f of x equal to 1 over 1 plus x squared. This particular function is actually super popular in calculus because this is the derivative of the inverse tangent of x. Deal with that some other time. We don't really care about it right now. So what we're looking for is an f1 of x and an f2 of x such that f of x is equal to f1 of f2 of x, or maybe the other way around, depending on what I assign to what. So I should look at it in its pieces. Well, for one thing, I've got 1 over stuff, right? That could be a function. So we'll say f of x is equal to 1 over x. And then I replace x with stuff, and I'll get my original function. So let me label this correctly. Say f1 of x is 1 over x. Then f2 of x is going to be whatever's inside of this form here. And inside of this form is the function 1 plus x squared. So I have 1 plus x squared in the denominator of a larger function. And if I were to compose these in just the right way, in fact, if I look at f1 of f2 of x is equal to f1 of f2 of x is 1 plus x squared, and f1 of x is 1 over x, so this is going to look like 1 over 1 plus x squared. So there we have, I've started with one function, f of x equal to 1 over 1 plus x squared, and I've successfully decomposed it into two easier looking functions, 1 over x and 1 plus x squared, which is a polynomial. So if I was looking for a derivative of 1 over 1 plus x squared in calculus, whenever that is, then all I really need to know is the derivative of 1 over x and the derivative of 1 plus x squared, both of which are very easy compared to what I would have to do with just f of x by itself. Now, I have some more we can work on. Let's see. I've chosen one that has an absolute value. So let's say we've got g of x equal to absolute value of 2x plus 1 squared. So I can see that on the inside of some stuff, I've got a 2x plus 1. That's probably one of my functions. And you can work from your inside and go out, or you can start from the outside and go in. It doesn't really matter. But let's say we noticed it in a different order. Let's see. g1 of x, I have stuff squared, right? So one of my functions is going to be x squared, and the stuff that I'm left with is the absolute value of 2x plus 1. So left over absolute value of 2x plus 1. Well, my next function as I work in is here I've got the absolute value of some stuff. Okay, so that'll be my next function, g2 of x will be the absolute value of x. But I'm still not done because I still have stuff on the inside, but what's left over is pretty simple. It's just 2x plus 1. So that'll be my third function. g3 of x is equal to, let's see, 2x plus 1. Now I could have done this in the opposite order. I could have started from the inside and say, hey, I've got one function here, which is 2x plus 1. And then I take the absolute value of that. That's another function. And then I square that. That's another function. So I could say I start with 2x plus 1, and then I take its absolute value, and then I square it. At any rate, the order has to be the same. So if we look at the composition g1 of g2 of g3 of x, always check your answers with this step. Ooh, a triple composition. Let's see, g1 of g2, and I'm filling in g3. g3 of x is 2x plus 1. If I plug that into g2, that's going to be the absolute value of 2x plus 1. Oops, got my bar there. And if I plug that into g1, this is going to be the absolute value of 2x plus 1 squared. So you see there you can have 2 or more. Now one of the problems with decomposition is there's some non-uniqueness. So if we do an aside here before the next problem, let's do it in blue. Oops. Let's consider p of x equal to x. So a lame little polynomial which is just x. I can decompose this function. In fact, I can decompose this into infinitely many component functions, which is kind of a dumb thing to do. But I can do p1 of x equal to x plus 1. And I can do p2 of x, which is equal to x minus 1. And then what happens when I do p1 of p2 of x? Well, I get p1 of x minus 1. And when I plug that into p1, well, that's x minus 1 in place of x plus 1, which simplifies down to x. And I can do a lame little trick like that for as long as I want. So there's a very large non-uniqueness problem with decompositions, although it doesn't really matter so much for us. And I can tack on an additional pair of component functions, +1, -1, +7, -7, or even a pair or a triple. I could do +7, -3, -4 for 3 different component functions, and then compose them all together and still get x by itself. Well, let's see, I've got another one here, and then we'll finish with an uglier looking one. Let's do r of x equal to the square root, square root of x squared plus 2 plus 4. That gives me, what should I do there? Let's start in the inside on this one. We'll do r1 of x equal to x squared plus 2, because that's inside of something else, which should make the other part square root of that stuff, my r1, is 4. Maybe I shouldn't have written it that way. Okay, so if I choose this for my r1, then what I should be writing is r of x is now equal to the square root of r1 of x plus 4. And that is what lines up my next function. So let's see, let's get rid of that. r2 of x, this is my stuff. So we're looking at square root of x plus 4. Now when I try to compose these, it looks like I'll have to do in the opposite order that I numbered them in, but r2 of r1 of x will be r2 of x squared plus 2, which is the square root of x squared plus 2 plus 4 as a final result. Now I've got another one we can do that way. One of my favorites. So let's see. I like how this one looks. What should we call it? H of x, because we hate it. Perfect. So I'm looking at, I've got the cube root of x plus 3, and that's all squared, plus the cube root of x plus 4. Supposedly I have to decompose this somehow. But what I can do is I can pull a similar trick to what I did in the previous problem. It was kind of hard to look at, so I picked something on the inside. See, this one works because outside of my square root, I just had some numbers, which is fine. They're like, whatever. I might have even been able to fit in another function in here, which was the square root of x. And then I could have had x squared plus 2. I could have had square root of x, and then I would have x squared plus 4 at the very end. It doesn't matter. That as long as you break it up, I'll count it. So here I want to identify something that counts as an inside function. And this is really the task when you're doing calculus, and the chain rule for derivatives is you want to choose something which is inside, something which is outside to help you with your decomposition. Now this one's kind of set up for us. On the inside of a pair of parentheses, I have cube root of x plus 3. So maybe I can count this as an inside. But the problem is I don't have cube root of x plus 3 anywhere else. But 4 is equal to 3 plus 1, right? So let me rewrite my function. I've got cube root of x plus 3 squared plus, I've got cube root of x. Instead of 4, I'm going to write plus 3 plus 1. Now what I'm looking at is I've got repeated instances of the same form or function. This is going to be one of my component functions. So let's say h1 of x is equal to this nasty cube root of x plus 3. Because then that makes my h of x look like h1 of x squared plus h1 of x plus 1. And that is definitely a composite function. So my h2 will be whatever I simplify this to. So h2 of x will be x squared plus x plus 1. And sure enough, if we were to check this, h2 of x, oops, I don't want h2 of x, h2 of h1 of x is equal to, this is going to be h2 of cube root of x plus 3, which is exactly, if I replace x in h2 with the cube root of x plus 3, I'll get cube root of x plus 3 squared plus cube root of x plus 3 plus 1, which is exactly what we started with. So this is something you probably definitely want to practice with. Certainly do the suggested problems for this section, although I don't think any of them are super necessary to do one way or the other. What we ended with is a fairly good strategy for attacking all kinds of decompositions. Is you want to identify something that counts as like an inside function, and then we try to simplify it in steps.